Good evening. In this video, we are going to discuss proposition 32 from book 1. Okay, so this proposition states that given any triangle, for example this, the exterior angle is equal to the sum of two opposite interior angles. Okay, so for example, this proposition states that angle ACD is equal to angle A plus angle B. Besides, it says that the sum of the interior angles of a triangle will be equal to two right angles, which means angle A plus angle B plus angle ACB will be equal to two right angles. Okay, so let's give them proofs one by one. First of all, please recall proposition 31 we've just proved. We are able to construct a straight line that is parallel to a given straight line and through a given point not on the straight line. Okay, so here let us suppose AB is a given straight line and C is a given point. So we can construct CE, which is parallel to AB. So CE is parallel to AB. And then please consider proposition 29. If two straight lines are parallel, then the alternate angles are equal and the exterior angle will be equal to the opposite interior angle. Okay, so we have, for example, these two straight lines are parallel and this angle and this angle are alternate. So we have angle ACE is equal to angle A, right? And besides, this is an exterior angle and this is one of the opposite interior angle. So we have ECD is equal to angle B, right? They are equal, right? And how we look at this angle, we can say that angle ACD is equal to angle ACE plus angle ECD, right? And if we apply common notion 1 to substitute these two angles with A and B, we know that angle ACD is equal to angle A plus angle B, which proves the first statement. The exterior angle is equal to the sum of the two opposite interior angles. And then let's try to prove the sum of three interior angles will be equal to two right angles. So think about this equality, sorry. We are able to add the same thing to both sides because of common notion 2, right? So let us add angle ACB to both sides. So we have angle ACD plus angle ACB will be equal to angle A plus angle B plus angle ACB, right? We plus ACB to both sides. And pay attention to proposition 13. We've proved two straight lines meet with each other, then the adjacent angles, the sum of them will be equal to two right angles, right? So these and these are two adjacent angles by the meeting of BD and AC. So we know that angle ACB plus angle ACD must be equal to two right angles. Okay, and when we combine them together and using common notion 1 again, things equal to the same are equal. So the right sides are equal, which means angle A plus angle B plus angle ACB is equal to two right angles. And this proves our second statement. So this is the end of our proof to this proposition. And we are actually able to extend proposition 32 from a triangle to a, let's say, to a convex rectilinear multilateral. Remember, it must be convex. This is important. And the sum of the interior angles would be, let me think, would be twice right angles as many as the number of the sides. Let's assume it is n. That's 4. So we subtract 4 right angles from it. This is the sum of the interior angles, and the sum of the exterior angles will be equal to 4 right angles. Okay? So in order to prove them, we are able to be honest, it's pretty straightforward. We can divide a convex, remember must be convex rectilinear multilateral into multiple triangles. For example, we can divide it into 1, 2, 3 different triangles, things like that. And this is the end of the video. In the next one, we are going to talk about proposition 33. Thanks for watching. Have a good day.